What is your definition of infinity?
It's a quote from Toy Story, to infinity and beyond.
What do you think infinity means?
I think that infinity means an incomprehensible idea of forever.
What do you think infinity is?
I think it's like a number that you can never get to.
What do you think infinity is?
Never ending.
What do you think infinity is?
A big number.
What do you think infinity is?
A number that goes on forever.
What do you think infinity is?
Yeah, well, I don't have a mathematical definition of infinity, though I'm sure there is one. But infinity is a number that is greater than any countable number.
Today I'm going to explain why there are different sizes of infinity. So the definitions that I got of infinity are a number greater than any assignable quantity or countable number, an unlimited extent of time, space, or quantity, something that is boundless, and a concept describing something without any bound or something larger than any natural number. And this over here is the sign for infinity. The concept of the infinity, as we now know it, was first mentioned by Anaximander, who was a 6th century before Common Era pre-Socratic Greek philosopher, and he came up with the theory about apeiron, which is the Greek word for infinity. Now we know that infinity is not a number, but it's a concept. There is no proof that infinity actually exists. It is a mathematical and philosophical term created to explain a concept that we don't fully understand. And this is Anaximander in a mosaic. Georg Cantor was born in 1845 and died in 1918, and he was one of the modern scientists that really kind of set in stone what infinity was. He was a German mathematician, and he developed set theory. And his work was very controversial because people didn't believe that there were actually different sizes of infinity. He spent his childhood in Russia, but then he studied at the University of Berlin, and he received the Sylvester Medal from the Royal Society in 1904, which is one of the highest honors they could give. So Cantor based his work partly off of Galileo's work with infinity. So one of the things that Galileo focused on was concentric circles, and he was trying to prove, well, you might think that a larger circle would have a larger number of infinite points around its circumference, because that's one of the things about a circle. It has an infinite number of points making up the shape. So we can see here that these strings kind of represent the circumference, and if we lay them out, it's clear that the larger circle has a much larger circumference. So we would definitely think that that larger line would have more points in it. But Galileo actually proved that they have the same number of infinite points, because if these are two circles and you take a line and you go around, this line is going to be intersecting exactly 1 point on each circle, and it's always intersecting exactly 1 point on each circle as it goes all the way around. So that way we can see that the circles actually have the same number of infinite points, even though one has a larger circumference. Another thing that you might originally think is that there would be more counting numbers, like 1, 2, 3, and so on, than even numbers, because it seems like there would be twice as many. But Galileo actually proved that there's the same amount, because if you match up 1 to 1 and you just keep going down the line, there would actually just be the same amount if you kept going until infinity. Just like if you had like a ton of people and you didn't want to count how many people, but you wanted to know if, for example, there was the same number of boys and girls, you could just ask each boy to pair up with each girl, and if there was the same amount, if there was an even number of pairs and no one left over, that would mean they were the same size. So we can kind of apply that principle, but just going on for infinity. So this actually kind of seems to disprove what Cantor was saying about there being different sizes of infinity. So this is his starting point, but he wants to prove that there actually are different sizes of infinity. So he used bijectures, which is where you pair on a one-to-one basis the counting numbers or the natural numbers with some other set of numbers to see if you can pair them up on a one-to-one basis. If you can pair them on a one-to-one basis, that means they would be the same size of infinity. So this works for natural numbers. It also works for rational numbers, so all of the fractions. It also works for even numbers or odd numbers or anything like that. You can always make a one-to-one pairing. But this doesn't work for real numbers, and we'll see why in the next slide. But this is kind of the definition of a countable infinity versus an uncountable infinity. So a countable infinity would be one where you can pair it on a one-to-one basis with the natural or counting numbers. But as we're going to see with the real numbers, we cannot pair them one-to-one, so they're going to be an uncountable infinity. Alright, so the reason why the real numbers don't pair on a one-to-one basis is that we can never come up with all of the real numbers that there are. Between 0 and 1, there's an infinite amount of real numbers just in there. So this is the diagonal proof, and it kind of explains why you can't pair them on a one-to-one basis. So basically what it's saying is that you can list some real numbers and say you could list a bajillion. You could list so many real numbers. So here's an example. They're listing some real numbers. But they're saying that you can always create a new real number that you don't have in any of your other lists just by taking the first term of this one, then the second term, the third term, the fourth term, and then you come up with this new decimal. And here they only have 4 places after the decimal point. But basically you could do this with as many places as it goes out and also as many numbers as you have listed, and you'll always come up with a new real number. So this means that you can't pair them on a one-to-one basis, which means that the real numbers are an uncountable infinity, and they're also a bigger infinity than the natural numbers.